So, today we want to move on to a different topic, which is games. Now, game playing has fascinated computer scientists ever since the beginning of computing time. Uh, Von Neumann was the first person to talk about chess playing programs, and we have discussed in the introduction that Alex Bernstein wrote a program in the early 50s, and Samuel wrote a program to play checkers, and so on and so forth essentially. Why do we like games? You can say games we like because they are well defined rules. So, if you solve real problems in the real world, if you want to solve computer vision or natural language processing or let us say TSP and things like that, some of those problems TSP is well defined, but some of the other problems are not so well defined essentially, the real world problems that you are trying to solve. Whereas games have clear cut rules, it tells you these are the moves you can make and so on essentially. Easy to evaluate. It is very easy to decide, the rules tell you when a player wins, when a player loses. So, it is easy to judge. Incidentally, the kind of games we are talking about, these are not the games which are popular amongst students, where you are shooting somebody or killing somebody. We are talking of simpler games, which are like chess and checkers and so on and so forth essentially. But the fact is that games, because of these two features, that they are well defined and easy to evaluate, are always a good medium for evaluating your reasoning algorithms or search algorithms or whatever is the technique that you are using. I mean, not only for us, but even in the real world, you can imagine that if you look at our country, you will find that politicians have their children who are politicians, that is their only merit, or film stars have children who become film stars, again that seems to be their only merit. Whereas, if you look at the world of sports, children of sportsmen do not necessarily make it big in the world of sports essentially. So, look at Sunil Gavaskar, one of the greatest batsmen we had. His son Rohan Gavaskar could barely make it to the Indian team essentially. Whereas, if he had been a politician, he would have been some big shot by now essentially. So, that is because games are easy to evaluate, that you do not have bias, you do not have judgment, somebody saying no, this is not good and that is good, there is no such thing, either you win or you lose essentially. Now, game playing derives from game theory. So, what is the name one associates with game theory? Who is credited with inventing this field of game theory? Not Nash essentially, but von Neumann is the person we credit with inventing game theory. And what do we mean by game theory? We mean rational choice in a multi-agent scenario. So, essentially game theory is the first place that we have stepped out of a single agent situation. So far the algorithms that we have looked at, search or whatever else, there was a single agent trying to solve a problem, and we were looking at what are the approaches to solve that problem. In game theory, we first time introduce more than one player, and therefore, we have to consider the actions of the other players essentially, and that has to be part of the reasoning process that you do essentially. Now, I wonder whether you have heard about this game called Prisoner's Dilemma. So, let me introduce this game to you in a more familiar setting. So, let us say there are two players as far as this game is concerned, and I am going to write the payoffs here. So, there are two players, and let us say in some hypothetical country, obviously not our country, there are two students who have been caught cheating, okay. And the dean has put them in two separate rooms, and they are being asked to confess whether they have helped each other cheat or not, obviously. And the payoffs are like this. So, let us say this is you, I mean you meaning not personally you, but the player for which you are designing this game, and let us say this is him, whatever, the other person essentially. And you have two choices, you have to confess or you have to deny. Likewise, the other player has two choices, you have to confess or you have to deny. When the game was originally defined, it was defined in terms of two crooks who were locked up in two different rooms, and the police was trying to interrogate them, and they had to confess or to deny, but the principle is the same essentially. So, what is the payoff here? Let us say these are your choices, confess or deny. So, if you confess and if the other person confesses, let us say you get a E grade, and this is symmetric for both. So, both people get E grades. If both of you deny, then let us say the payoff is this, you both get D grades because nothing is proved or something like that. Now, if you confess and the opponent, if you want to call the person opponent, denies, then let us say you get a B grade and the opponent gets an F grade. Okay. Likewise, if you deny and the opponent confesses, then you get an F and the opponent gets a B grade. So, the top right corner is your grade, the bottom left corner is the other person's grade, and these are the four possible situations: you confess or you deny, the opponent confesses or the opponent denies. You can construct a tree out of this to represent this choice. Now, remember that this is a game which is played where you have to decide, sitting alone in a room and you are being interrogated by somebody, you have to either confess or you have to deny, and you know the payoff matrix. Both players know the payoff matrix. What is the correct strategy to use here? Game theory is concerned with questions like this, that if you know the consequences of your actions in the context of other people's actions, what are the choices that you will make. So, in this situation, do you think it is good to confess or is it good to deny? Rationally speaking, sorry, you have to speak a bit louder. Deny is better. Why is it?
I confess there is a risk of an F.
See, let me explain this matrix again. The first, look at the first square here on the left hand side, it says that you are confessing and the other person is also confessing. You do not know what the other person is doing, but if the other person also confesses, then you get an E and the other person gets an E. This square says that if you deny and the other person confesses, then you get an F, let us say F stands for fail, and B, other person gets a B essentially. If you confess and he denies, then it is symmetrically opposite, you get a B and he gets an F. If both of you deny, then you get a D each essentially. What should be your strategy?
Confess.
How many people say confess and how many say deny? So, others do not have an opinion. So,
If you confess and the other denies, it should be opposite.
Sorry.
If you confess and the other denies, you should the other person should get a B, because in this case the denying is bad in both the cases, irrespective of whatever he says.
No, I can't see. Yeah, okay. So, if you look at this other scenario, let us say two people have robbed a bank or something like that. I don't know which is worse, whether cheating in a class or robbing in a bank, but anyway, let us say they have robbed the bank. And then the police is interrogating the two people separately. They say, okay, if you confess, we will let you off lightly, but the other guy will get the punishment. So, it is in that sense that you help them establish that there was a crime essentially. So, it is in that sense. So, that is why if you confess and the other person denies, you are let off with a B, but the other person gets an F essentially. And otherwise, if you deny and other person confesses, it is the other way around essentially. So, many people said confess. Why is confess good? So, we should give a rational argument. Game theory is about rational behavior, that what is logically the correct thing to do essentially. You want to maximize your grade in this case, or in the case of those robbers, they want to minimize their punishment, but the problems are equivalent essentially.
Irrespective of what the other guy does, it's better for you to confess.
Yeah, but I just that okay. Let us say your answer is correct, but I just don't want the answer. I want an explanation.
If you deny, you have a greater risk of getting an F. But if you confess, you can get a B and an A, which is better than F.
If other person is denying, we will get a better grade. If other person is confessing also.
So, I will encourage you to draw a small tree out of it. So, for example, you confess, deny, and then the other person confesses and denies, or you can construct it like the other person confesses and denies, and then you confess and deny. You can construct a tree both ways and then explore that essentially.
In either case, if you take the situation where whatever, regardless of what the other person does, if you see the corresponding row, your choice is between confessing and denying. In one case it is between E and F, in the other case it is between B and D, so it's always better to take the choice of confessing.
So, let us argue, let us just expand upon that argument and say that, let us say if you confess, what will happen? That means you are looking at this row essentially. You are looking at the first column. If this person confesses, then you get an E. If this person denies, then you get a B. Which is, so this looking at this thing is looking at this T structure. First you look at your decision and then you look at the other two decisions and then see which one is better. You will see that in this case this is better. In this case this is better and this is bad. If you deny, if the other person confesses, you get an F, and if the other person denies, you get a D. So, maybe this is actually, yeah, this is little, maybe let us look at the other side of the argument. If the other person confesses, what should you do? If the other person confesses, so we are looking at a row now. So, we are looking at this tree. You can argue on this tree also, but let us look at this. Maybe this is simpler. If the other person confesses, you are looking at this row. If you confess, you will get an E. If you deny, you will get an F. So, if the other person confesses, it is better for you to confess. Correct? You are looking only at the row. If the other person denies, if you confess, you will get a B. If you deny, you will get a D. So, even in this case, it is better for you to confess. So, it is better for you to confess in both cases actually. So, if you look at, if you construct a tree like this, where you consider the other person's choices first and then your choices, you will see that your choices, this is better and this is better. In this case, these two are better and these two are worse essentially. But This way it is easier to evaluate. Yeah, the rational choice is to confess, and assuming that the other person is also rational, the other person will also confess. So, your expected grade would be an E essentially. This E is called the Nash equilibrium in this game, which means that if you deviate from this, or rather the other person cannot deviate from it without spoiling the game for him essentially. So, such an equilibrium is called a Nash equilibrium. But is this the best outcome? It is not the best outcome in this particular matrix, because if both of them were die-hard people, I am not saying that students can be die-hard criminals, but we are talking about those robbers now. If both of them are die-hard criminals, like for example, it is eulogized in many films essentially. So, yeah, there are these two criminals who are really good guys, but they will never confess to anything. Now, if you have two such people and they have trust in each other in some sense, then they will both deny, and in this matrix they will both end up in this lower right hand corner, which is a better situation than that situation. So, this of course is called a Pareto optimal, but it is not a stable optimal with this problem situation. If I were to exchange these grades for these two corners, this EE and DD, then the Pareto optimal coincides with the Nash equilibrium, and then it is really the best solution essentially. But so why is it called a Nash equilibrium? Because in some sense, if you confess, the opponent is forced to confess. If he does not confess, then he will be worse off. Likewise, if he confesses, then you are forced to confess essentially. Now, obviously, you cannot get into complicated, or you can try to get into complicated kind of reasoning that I can figure out that it's anyway. So, this is a basic idea of game theory, puts you in situations like this, and it's a basic mechanism for study in economics when people try to evaluate things like what should be the pricing mechanism, how much should you advertise and things like that. People use game theoretical concepts to reason there essentially. So, rational choice in the case of multi-agent scenarios essentially. So, you can think of price wars, for example, as a game between two players. So, let us first characterize games a little bit. The kind of games that we are going to be interested in are much simpler in nature. These are called board games, and as the name suggests, they are played on a board like chess, for example. In particular, the games that we will be interested in have these following characteristics. They are two player games, which means that there are only two players in this game, but there can be multiplayer games. Maybe we will give an example or two. Zero sum So, we will be interested in games which satisfy this property: two players, zero sum, alternate moves, deterministic games. I might even say discrete games, in the sense that things like chess and so on, where you have to choose between a discrete set of choices. So, two player basically says that there are two players, but you can have a multiplayer game essentially. So, I was just talking about price wars. So, if you think of price wars as a two player game, which means let us say Pepsi and Coke are getting into a price war, they are both decreasing prices to get more market share, then you can think of it as a two player game, and you can also think of it as a negative sum game, which means that both the players are going to lose out on the money that they get essentially. So, a zero sum game is a game in which the sum of the payoffs of different players is 0. So, chess, for example, one person wins, the other person loses. So, if 0 stands for a draw and -1 stands for a loss and +1 stands for a win, then the total sum is always 0 essentially. One person's gain is another person's loss. So, these are games of course, where you have opponents essentially, but there can be games when there is negative sum. So, for example, this game is a negative sum game actually, assuming that E and D are negative things which you do not particularly like, or the price war game is a negative sum game, because the revenue of both the companies is going to suffer a loss which is seen as negative essentially. But you can also have positive sum games, for example, cooperation between people. If two people sit down and study together for an exam, then both of them gain from it essentially. So, you can have different degrees of games essentially. So, price war, as I said, can be seen as a 2-player negative sum game, but if you include the third person, which is the consumer, then it becomes a 3-player game. So, let us say there is one figurative consumer, and then it becomes a 0-sum game, because whatever the companies lose, the consumer gains in terms of price we are talking here. Okay, I missed out on very important characteristic, which is complete information. In complete information games, each player knows what are the moves available to the other player essentially, what are the choices available to the other player essentially. So, obviously, the games that we have been talking about like chess and checkers and cross and knots or Go, or this game called Othello, which you are going to do an assignment on. These are board games on which you can see the board, both sides can see the board, and therefore, they are complete information games essentially. But there are many incomplete information games. So, games like card games, for example, games like bridge or poker are incomplete information games, but there are also games which are deterministic versus non-deterministic. So, for example, if you have to throw a dice in a game like backgammon or Ludo or something like that, then that is not a deterministic game, whereas you cannot predict the outcome of a move essentially. So, backgammon, for example, is a 2-player 0-sum alternate move stochastic incomplete information game. The moment the game becomes stochastic, it becomes incomplete information, because you do not know what happens when you roll a die or when the opponent rolls a die essentially. Of course, in the real world, many situations where you have to do rational decision making, you are mostly operating in an incomplete information world essentially. An extreme example are two generals who are fighting a war essentially. Okay. So, you do not really know what the other army is doing, which side they are moving, and of course, you try to have spies on the other side and you try to have intelligence, and maybe you take satellite images and all kinds of stuff, but that is a effort to move towards a complete information situation. But in practice, of course, you have to work when the information is not complete essentially. And alternate move games are essentially the simpler kind of games in which I make a move, then you make a move, then I make a move, and then you make a move, which are easier to model for us essentially. Now, the moment I talk of alternate moves, you can see that we are moving away from these kind of games where there is only one decision to be made and you have to just make one decision. Here, typically you have a sequence of decisions. I make a decision, then you make a decision, and then I make a decision, and things like that essentially. So, such games can be represented by a game tree. A game tree is a layered tree So, let me draw one, and typically because we are talking of 2-person games, there are two kinds of nodes, one for one player and one the other kind for the other player, and typically we draw them differently. So, this is a root node which the first player has to make a move, and let us say this is one move that this player makes out of the many possible moves. Then the other player makes a move, then the first player makes a move again, then the other player makes a move, and so on. So, this is a game which is it's a actual game played, which says that one player made this move, then the second player made this move, then the first player made this move, and the second player made this move. So, square is one player and the circle is another player essentially. But of course, there are many choices that they all have. So, in practice it is a tree. So, something like this. So, such a tree is called a game tree. It is a layered tree where each layer represents the choice for one player. So, this is some tree I have drawn randomly. Okay. Traditionally, this player is called max and this player is called min. And you can see that the tree basically represents a sequence of choices for both players. We are assuming that max plays first. So, max has to choose between these 3 moves, then depending on what max chooses, min has to choose between 2 moves and so on and so forth. So, such a tree is called a game tree, and in a game tree leaves are finished games. So, a leaf represents end of that game and it has got 3 kinds of labels. So, a leaf may be labeled by one of these 3 labels: win, draw or loss, and this word is from max's perspective. So, when we say win, it means max has won the game, and if we say loss, that means max has lost the game essentially. So, this is for max. Everything that we do is for max essentially. So, labels are from max and so on. So, we can compress this to W, D or L essentially. So, let us label this arbitrarily. So, let us say this is L, this is D, this is D, this is W, this is L, W, D, D, L. Every leaf must be labeled. So, every leaf has a label. So, basically the game tree represents all possible games that can be played given the rules of the game. So, when we draw the game tree, we do not talk about rules, we just say okay, this is a game tree. So, you can imagine that if you were to draw a game tree for chess and white starts first. So, white has a set of moves that white can make, which is 8 plus 8, 16 pawn moves plus 4 knight moves. So, those of you who know chess, at the top level white can make 20 moves essentially. So, you could just draw the tree and say okay, forget about the rules of the game essentially. So, a game tree is basically a representation of the rules of the game, and once we represent the game in the form of a game tree, we can just reason with the game tree essentially. Now, every game has a outcome which will be the outcome if both players are playing perfectly. So, we are always interested in rational choice. Remember, we do not want to play against an opponent who makes mistakes and things like that. We assume that the opponent is perfect and our analysis is based on that essentially. So, if both the players are perfect, then every game, and a game tree is a finite tree, because it has all these leaves, has an outcome which can be computed essentially. So, just like, so you can think of this as a game tree with only one node essentially, and its outcome will be determined by what choice you make essentially. At the same time, this is simultaneous, it is not alternate move essentially. Both the players are making moves simultaneously, whereas the games we are talking about, first Max makes a move, then Min makes a move, then Max makes like chess for example, and so on. So, how do we this thing? The outcome is called the Minimax value. Is equal to outcome of perfect play on both sides. And by perfect play we mean that each player is making the correct choice essentially. So, let me ask you, for example, you are familiar with noughts and crosses, right? This game which children play, or tic tac toe also as it is called. So, you put one cross, somebody puts a knot, you put another cross and so on and so forth, right. You are familiar with this game. So, let me ask you, what is the value of this game, or what is the minimax value of this game? It is draw, right, which means that everybody knows that if we play it perfectly, then the game is a draw. So, how would we compute the value, minimax value of a game? Is that we would have a backup rule which would back up values from bottom to top, and the backup rule will basically look at the kind of node that it is. So, I will not write the rule, I will just state it here. So, for min, it means if you can back up L, if one of the choices is L, then back up L. If none of the choices is L, then if you have a D, you back up D, otherwise you back up W, you are forced to back up W in some sense, because min, the desired outcome for min is a leaf labeled L, because min wants to win the game, which means Max should lose the game. So, therefore, min is trying to drive the game towards L. So, you can see what is happening here. The first move is made by Max. So, let us say Max makes this move, then it means it is up to min. So, min will try to drive the game towards L. So, for example, there are some L's here, but if min drives the game here, unfortunately I have drawn both of them like this. So, let us say this is L. If min drives the game here, you can see Max can choose W and end the game there. So, it is better for min to play this move. So, if min plays this move, then Max will not choose that, of course, no, and Max will choose this, and at this stage min can win the game. So, you can see that if min makes this move, then min can win the game, which means Max should not really make this move essentially, because perfect min will win from here essentially. So, this kind of analysis is simplified by this backup rule, which says that you back up from leaf to the roots, and for min you choose. So, so for min the order of preference is this, for Max it is this, which means a min will prefer L to a D. If it can see an L and a D, it will take L. If you whatever, it will always choose the rightmost, Max will choose the leftmost. So, as we will see, it helps to think of this as a supply chain kind of a thing, where Max is applying some values to min, and min will choose, and min's choices always prefers L, and then D and then W. Likewise, min is making offers to Max, and Max will choose, and so on and so forth. So, before I fill up the tree, let me also say that we can represent this by 1 or 0 or minus 1 as well, just a numerical way of representing these outcomes. which of course gives us a clue as to why max is called max and why min is called min, because max is driving it towards 1, trying to maximize the value of the game, and min is trying to drive it towards 0, or sorry, towards -1 and trying to minimize the value of the game. So, that is why the players are called max and min. So, in terms of numerical values, it is easier to state the backup rule. Max chooses the maximum of the values available to it, and min chooses the minimum of the values available to it essentially. And what do you mean by available to it? That's from the next layer what is being supplied to it essentially. So, let us fill up this tree. So, this is L, this is D. So, min will choose L here, this is D, this is W, min will choose a D here. This is L, this is D, so max will choose a D here. This is, both these are D, so min does not have a choice. Here it is L, and so this is, there is only one node, so this gets backed up L. Max will choose W here, and we analyzed this part of the tree earlier, right. Min will choose L here, max does not have a choice, so max has to choose L here, min will choose L here. Here max will choose W between W and L, min will choose D from this. So, at the top level you can see that max has 3 choices, one of them leads to a node which will evaluate to eventually will evaluate to a draw, this move will eventually lead to a loss, and this move will eventually lead to a draw. So, max can choose one of those other 2 moves rationally speaking, and the minimax value of the game is therefore D. So, this is a game which has a minimax value of D essentially. So, in some sense solving a game amounts to trying to find the minimax value of the game. It is called minimax because at alternate layers you are minimizing and maximizing essentially. So, in some sense you are trying to this thing. Another way to put it is that we are trying to find a strategy for max. So, obviously at the first level we have known that max should make either this move or this move, but on what basis are you saying that, and that basis can be formalized in the notion of a strategy, and a strategy, we are talking about max at this moment, but we can talk similarly about mix for min, is a subtree which is constructed as follows, that one choice for max and all choices min. So, by strategy we mean that max is freezing max's choices and saying this is my strategy, this is how I am going to play this game essentially, which means that at every place in the game max says that this is the choice I will make. So, that is why the strategy is a subtree that we construct by making one choice for max and all choices for min. Why all choices for min? Because it is max's strategy and max does not know what min will play essentially. So, max has to account for or cater to all of min's choices. So, the strategy must consider all of min's choices. So, we can draw a strategy for max. So, one strategy is, let us say this one. Now, we have chosen this, but for this we must choose both, because all choices for min. Then we can have this choice for max, and let us say this choice for min, and so this is the thick lines represents one strategy for max. Of course, this max has access to many different strategies, and you can say that the task is to find the best strategy for max essentially. So, let us draw another strategy for max, which is on this left side of the tree. So, max could have chosen this move, and then of course, you have to choose both these moves. Then max could have chosen, let us say, this move, which is a better move, and then min would have chosen. So, that is how you construct a strategy. At max level you choose all, sorry, at max level you choose one choice for max, and at min level you choose all choices for max. And what the strategy gives you is a set of leaves. Yeah. Every strategy has a set of leaf nodes which tell you about this is what will happen if max chooses this strategy. So, the question I want to ask you is, given a strategy, how do we evaluate a strategy? Let us work with this one, numerical representation. Let us say the leaves are labeled with 1, 0 and -1. So, given a strategy S and I talk about a value of a strategy, how can I compute the value of a strategy?
The strategy.
Worst possible one, and by that we mean the lowest value. So, if you look at this white strategy, in this white strategy the leaves have W, D, D, L, four nodes in the leaves, and the worst of them is L or -1. So, that is the value of this strategy. If max chooses this strategy, he will end up losing the game. If min is perfect, because the choices that are left are only for min essentially. So, if min is the perfect player, then if max chooses this strategy represented by this tree, then max will end up losing the game. And the value of the strategy is the lowest value of the leaf nodes essentially. If you look at this strategy, then you can see that there are 3 leaf nodes here, D, D and W. The worst of them is D, and therefore, the value of this strategy is D. Or 0 in this case. If you are looking at -1, 0 and 1, the value of the strategy is 0. Now, none of them is a winning strategy. A winning strategy would be a strategy whose value was 1 essentially. So, ideally of course, you want to find a winning strategy for a player or max in this case, because we are writing the program for max, let us say, and somebody else is handling min. Or if you cannot find a winning strategy, then at least you should prefer blue one essentially. So, I will leave you with this question here. Can we think of this as an AND OR tree, and can we use AO star algorithm to find an optimal strategy? Because you can see that this is like an OR choice and this is like an AND choice. This is like an OR choice and this is like an AND choice. So, can we think of it as an AND OR tree, and can we use the AO star algorithm? So, I will stop here, and in the next class we will take it up from here eventually.